Let's talk about the derivatives and integrals of hyperbolic functions. And again, we're essentially following the analogy we have with trigonometric functions, though it's not quite the same. It's actually simpler in this case because there's no negatives, right? So we have the derivative of cosh is sinh, and the derivative of sinh is cosh, which tells us that the integral of sinh is cosh, and the integral of cosh is sinh. So really, it's just a nice additional piece of machinery that we can use in taking our integrals and derivatives. We also have the derivative of tanh is hyperbolic secant squared, and the integral of hyperbolic secant squared is then tanh. I don't know what the shorthand, how to say this, other than saying hyperbolic secant. I don't even know what it would be. Maybe there's a word out there for it. And then there's more, right? So then we do get into some negatives. Derivative of hyperbolic cotangent is negative hyperbolic cosecant squared, and so on, right? As we'll see, hyperbolic functions give us a bountiful list of various integrals and derivatives that we can have. There's more when we get into like inverse hyperbolic trig stuff. And are we expected to know all that? Not really. What I would say is know these first three, cosh, sinh, and tanh, and the corresponding sinh, cosh, and hyperbolic secant squared. And maybe 4, 5, and 6 you could know, but I would certainly expect you to kind of look those up if you saw them in the field or something like that. That wouldn't show up on an exam of something that you should just have memorized for these 4, 5, and 6. And anything beyond that, I would say you would just look up in an integral table or use some kind of computer calculator to work these integrals. The point of calculus is not to just sit around and memorize an ever-expanding list of integrals, right? There are entire books of integrals. So that's certainly not the spirit. So let's just focus on the first three and see if we can take some derivatives and do some integrals from there. But first off, I want to prove one of these things. Let's prove number 2. And I would like for you to try this. I think you can do it. But first, let me bring up the definition of sinh, just in case we don't have it memorized yet. Okay, so remember that sinh is e to the x minus e to the minus x over 2. Pause the video, see if you can prove that the derivative of sinh is indeed equal to cosh. Okay, let's take a look together. So here's the proof, right? We essentially have the derivative, d by dx, of e to the x minus e to the minus x all over 2. Well, this 1/2 comes out to the front, and then we're left with the derivative of e to the x, which is e to the x. The derivative of e to the minus x is minus e to the minus x, but then a minus, so we could write this as minus e to the minus x. And that rounds us out nicely. We are indeed left with e to the x plus e to the minus x all over 2, which is indeed cosh x, completing the proof. So, again, we're just having fun with these proofs. Let's try computing a couple derivatives, and then we'll work on a couple of integrals as well. Here we're asked to find the derivatives of f of x equals e to the x times cosh x for part A, and f of t equals natural log of sinh t for part B. So I think you can do both of these. Pause the video, try them out, and then we'll compare notes. Okay, well for A, we're going to hit this thing with the product rule. So then f prime of x is a prime b plus b prime a. That's the product rule. A prime is e to the x prime, which is e to the x, times cosh x, that's b, plus b prime, sinh x. Remember, there's no negative there. So sinh x times e to the x again, a. And maybe it makes sense to factor out the e to the x. I don't know if that makes it a ton better, but perhaps it does. So e to the x cosh x plus sinh x. I guess that's a little bit simpler, but really that's about as good as it gets. Okay, part B, f of t equals natural log of sinh t. Let's take that derivative. F prime of t is, all right, derivative of natural log is 1 over whatever's inside it. It's 1 over sinh t times the derivative of the inside. Well, the derivative of sinh is cosh t. So we really have cosh t over sinh t, which happens to be hyperbolic cotangent. So cot h of t. There we go. Okay, and so on, right? You can imagine we could add more and more complex derivatives and just keep applying the same rules of differentiation that we already know and love, and keep computing derivatives with these things. Let's try some integrals. Here we have 3 integrals to work, and I think you have all the skills to work each one of these, so let's try them on your own. Let's start with part A, and then we'll do part A together, and then part B, and then we'll do it together, and then C, and then we'll do that together. So for part A, we have the integral of hyperbolic secant squared over 2 plus tanh x dx. Pause the video, try that on your own, see what you get. Okay, well perhaps you noticed that this was a u-substitution. How about if we let u be, let's put a u in there, let u be, how about 2 plus tanh x, right? We're trying to cover everything up with a u and the du. Well, this works out nicely because then du is hyperbolic secant squared x dx, and we've covered everything, right? There's our, all of this is our du, right? And then our u is down here. So this whole thing becomes the integral of 1 over u du, which we know is natural log absolute value of u plus c, but u is 2 plus tanh x, so natural log absolute value of 2 plus tanh x plus c. So if you're super solid on your integrals using the trigonometric functions, the hyperbolic function integrals will follow quite naturally. Let's take a look at B. We have the integral of cosh cubed of 3x times sinh of 3x. Again, pause the video, see if you can work through that, and then we'll work it together. So here we see a lot of analogies with the trigonometric functions. How about we let u be, how about cosh? Cosh of 3x. All right, how's that looking? Then du will be sinh of 3x times 3, derivative of the inside, so I'm just going to bring that 3 to the front. 3 sinh dx, 3 sinh 3x dx. So then we can solve this for dx. dx then must be du over 3 sinh 3x. Plugging all this in gives us the integral. Well, the important thing is we're going to have this 3 down in the denominator, so I'm just going to bring that out to the front of the integral. There we go, and what do we get? U cubed du. Okay, then the power rule for integrals tells us to raise this to the 4th power and divide by 4. That gives us 1/12 u to the 4th plus c. But of course we need to plug in for u, so we get 1/12 cosh 3x plus c, or you could write this as cosh 3x over 12. Okay, moving on to part C. Let's clear out some room here. We have the integral from 0 to natural log 2 of tanh x dx. If you recall, tanh wasn't one of our readily available integrals. Pause the video, see if you can figure out how we can work this. Okay, well how about this? What if we wrote this integral instead as the integral of 0 to natural log of 2 of sinh x over cosh x? That's a standard way to approach the integral of tangent. So the more times you see it, the more you'll kind of recognize that's how to proceed. And now we need a u and a du. Well, if we let u be sinh, we're going to end up with a du down in the denominator of cosh. And you can't ever have your du in the denominator. So sometimes you're like, which one do I choose? Choose whichever one gives you a du up in the numerator. So that tells us that we're going to let our cosh be our du, or I'm sorry, our u. So let u be cosh x. And of course, du is sinh x. Oops. Sinh x dx, which is the entire numerator there. Okay, so our new integral is the integral, we'll deal with the limits of integration in a minute here, of 1 over u du, or simply du over u is another way of saying that. Okay, and that's something we definitely know how to integrate, but let's deal with these limits of integration here. I'm just going to treat u like a function. U of 0 is cosh 0. Cosh of 0. Well, I don't remember what that is. That's okay. I'm going to use the definition of cosh. That's e to the 0 plus e to the minus 0 all over 2. 1 plus 1 over 2, which is 1. So this integral goes from 1 to something. Let's look at the second limit of integration. We have u of natural log 2. Okay, well, e to the natural log 2 plus e to the minus natural log 2 all over 2. Well, e to the natural log of 2, the e and the natural log undo each other. So we have 2 plus, now one thing happens here. This negative comes up into the exponent like so as a negative 1. So we have e to the natural log of 2 to the negative 1. I'm just going to rewrite that as e to the natural log of 1/2. Okay, so that's kind of the stumbling block that you have to make sure you can get over here. So 2 plus 1/2 over 2. Well, this is, let's see, 5/2 over 2, which is 5/4. Okay, so there's our upper limit of integration, 5/4. And we're off. The integral of 1 over u du is natural log of absolute value of u as we go from 1 to 5/4. Well, you can see we're positive here, so actually the absolute value isn't necessary, but so be it. Natural log of 5/4 minus natural log of 1. Well, natural log of 1 is 0. How nice. So we're left with simply natural log of 5/4.